Okay, so last time we were here, we looked at probability. We learned some definitions. For example, we learned the definition of sample space. Sample space is simply the what? Total number of outcomes that are possible, right? We talked about an event. An event is just what you're measuring. So like if you roll a die and get a 6, that's an event, right? And we talked about the notation. Probability of an event is P in front of a bracket with the event inside. And we said that because the word of always means multiply. And if you have two things side by side, a bracket and something right in front of a bracket, that means multiply. Probability of. We talked a little bit about the notations. It can be a fraction, or it can be a decimal, or it can be written as a percent, right? Okay. Only percent when they specifically ask you for it. Now, so what we're going to do is continue our talk about that, and then we're going to add something called expectation, because a probability on its own really doesn't do you any good. So we want to find out. We're going to look at some uses of probability and why we look at probability. Okay. All right. So let's begin. Okay. We also talked about. Just go through these real quickly. The probability of 0, that all probability is between 0 and what? 1. With 0 being impossible to happen and 1 being certain to happen, right? And all probability has to be between 0 and 1. It can be 0 and 1, but it's usually something between, okay? Good deal. And the notations, so they're written. We're just going to go through this real quickly. So, and outcomes are equally likely, right? So when we're talking about these things, this only works if they're equally likely, which means they're not fixed. And it's the number of correct outcomes or favorable ones over all of the total number possible. These are all the things we went through last time, just getting to where we were. All right? And then we talked about making sure you include all the information. If it's the numbers 4 or more, that includes the 4. What if I said the number's bigger than 4? Not including the 4, just anything that's bigger. There you go. Good job. All right. So let's look at experimental probability. Now, experimental probability means instead of just thinking about the numbers and using what we know about the numbers, we're actually going to physically do an experiment. Okay. And so if I just thought about rolling a die, that's what? Theoretical, right? But if I took the die and physically rolled it, that's experimental. And at some point, if you did the experiment enough times, experimental probability and theoretical probability would merge or become very, very, very close. Okay? But again, it takes thousands or perhaps even millions of experiments for that to happen. So, don't expect it to happen if you decide to compare the two. All right? So, the formula for experimental probability is identical for theoretical. There is no difference between the two. The number of times an event occurs, in other words, a success. So, you determine your success. So, let's say I want to roll a 4. Then rolling a 4 is a success. Rolling a 3 is not, right? So you'll just tally up the times you get the successes, right? You're only counting the times that it works. And that definition of works is determined by what event you want to happen. And again, event means getting the thing you want. So if I want a 6 and I roll a 5, I don't want that, right? I wouldn't count that. Out of the total number of trials, the total number of times you did it. Okay? Total number of things you have happening. So as the number of trials increases, the probability will approach the constant value or the actual probability. I just told you that. I'm not going to tell you that again. So here we go. Now, Zane is curious to find out if the probability that he'll hit a golf ball across the room into a cup. Okay? He hits the golf ball 50 times, and 22 times the ball lands in a cup. Find the probability that his next shot goes in. So, I already know parts of it. So what I want is the probability, I want the probability that the ball goes in the cup, right? Now you could say it differently. You could have put just probability of cup or whatever. So the words you use there might change, but make sure it's descriptive, that you can actually tell what it is you're measuring. And I already know that these probabilities are always going to start off as life as a fraction, right, when we're finding them. So how many times did he hit the ball? 50 times. So that's the total number of trials, right? So out of 50. Make sense? Yeah. And how many times did he successfully get the ball into the cup? 22. So that's the number of times he was successful. So 22 out of 50. Am I done? No. No way. Exactly. Remember, even if you don't change it to a decimal and you want to leave it as a fraction, you never leave a fraction without simplifying it. So both of these numbers will at least divide by 2, right? So you'll get 11 over 25. Will that simplify any further? No. So the probability that he's going to get it in the cup is 11 over 25, which you could change into a decimal if you want, if you like them. Yes?
Should we write that down as an example?
You can write that down as an example, sure. If you want to use, because some of you are concerned about not using your example space enough, sure. So you can write that down as an example, but also we're going to be doing some examples in class together too. So yeah, you can never write down too many examples, right?
Unless you fill up the page and you have to use the next one.
Yeah, then, yeah.
That's a real problem.
But on probability, it's not going to happen very often because there's not that much you're writing, right? That didn't take too much space. Okay? So, now, they did something I don't like. So look at their solution. Here's what I don't like. Why?
It's not giving you any description about what you're actually talking about.
Exactly. We don't know what you're measuring. Probability of A, that could mean the probability that he just didn't go to work that day, right? Who knows? I want you to be specific unless they tell you to do that. Does that make sense? If they tell you to let A be the probability, then you need to write probability of A. But if it just says find the probability, I want you to be specific. Okay? Can you use abbreviations? Sure. Can you use initials? That's fine. But be specific. Be specific enough so that someone reading your paper, not me, right? Because just someone else is reading your paper will know what you're talking about. Okay? By seeing the original problem and what you wrote. Okay. But if it says specifically let A be that, and you typed in probability of in the cup, guess what's going to happen? Yep. Mm-hmm. It's going to tell you you're wrong, and you're going to be going, why? My math is perfect. It's because of the notation. Okay? Yeah. Well, but remember also on the assessments, it could do that too. So get used to it. One of the things that kills students in statistics, and probability is part of statistics, well, you know what I mean, is that,
No, I don't.
Okay, one that causes trouble for students is notation. Notation is incredibly important here. Okay? All right. You can also write it as a decimal or a percent. Is there any point in it? No. Now, I'm lazy. Tell you that right now. So if I got this and I knew it reduced, I'd just put that in my calculator and get that. Problem with it, though, is what if it was a repeating decimal? Then I'd have to round it. That's not good. So be careful. So so just think about what happens here. If this is like a 3 or something, then you're going to get a repeating decimal. So use your own discretion. Y'all are not lazy, so y'all can just reduce fractions all day long. Okay? All right. All right, so let's do another one. Here we go. Oops, sorry. I want to just move that down. A group of 50 year 12 students. Now we're going to do this one. Y'all are going to do this, and then I'm going to ask you questions about it. So this one you're going to write down. Make sure you're writing this down. A group of 50 year 12 students were surveyed, and it was revealed that 20 of them had an iPad. If we select a student at random, then the experimental probability of having an iPad is. So, go. Find the probability that a student in this group has an iPad. Yeah, probably doesn't take very long. Give you a minute to finish while I. Amy, was there one more person absent? Amy? Christiana Focus, right? Okay. Is that right? Oh, Tina, yeah. So we had 3 girls, okay. All right, everybody got an answer of some sort? Okay. What I want to do is I want to walk you through, this is the way we're going to ask questions, right? So, we're finding the experimental probability of something. So the first thing I need to do then is I need to write it out. So, Claudia, where are you, Claudia? Hi, Claudia. So, Claudia, I'm going to write probability, bracket, what do you want to say? Has iPad? Yeah, and you don't, yeah. So you could put probability has an iPad, or you could just put probability iPad, because what would you write if it was you were measuring the other way? Maybe not iPad. You really only have to be specific if it's not, right? Because if you say probability of iPad, your brain's going to think, well, I want to know who has one, right? But if it's not iPad, then you might write ad. But it's not wrong if you write more. Okay? Good job. Okay? So everybody see what I'm doing now when I call on you? I'm just going to have you ask, and the math here hopefully is pretty good, and I'm going to explain. Nova!
She's over there.
Nova, okay? So I'm going to always write probability as a, start it out when you're doing it as a, what kind of number? Starts with an F? At the bar, so as a fraction, right? A fraction. There we go. Okay, I'm going to always start off writing them as a fraction. So I need 2 parts, and the top part is the number of successes. The bottom part is the total number of trials. So Monique, look at that, how convenient. Monique, can you tell me? It says out of a group of 50 year 12 students, and 20 of them had iPads. Which one of those is the total number that goes on the bottom? The 50. Excellent. All right. Am I walking you through this easy enough that you're not scared to answer my questions, hopefully? I hope. Okay. Later, I'm not going to give you so much scaffolding, right? I'm going to expect you to be a little more on your own. But for now, we're fine. But if you tell me I'm not sure or whatever, then that's what I'll do. I'll give you more scaffolding. Bo.
Hi.
There you are. Bo, sorry. I knew you were over there, but I couldn't. All right, Bo. Then I need another number. The top number represents the number of successes. In this case, the number of people who actually had iPads. How many was that in this case? 20. So that's going to be my numerator, my top number. All right? It's good? Okay. Remy? So, Remy, am I done now?
No, you can simplify.
I can simplify that, right? And this one's extremely easy to simplify because they both end in 0, which just means the zeros are going to divide away. And then, Bua, what is that going to leave me with? Probability of an iPad is 2/5? Or 2/5? Could you have changed that into a decimal?
Yes.
Perfectly fine with me. Don't care.
Okay. I don't.
Okay? All right? So, how does that look? How did the questioning feel? Are you just still terrifying of it? I'm not doing it to make you crazy. I'm doing it to make sure that we're all paying attention and we're all on the same page. Okay? And that because too many times students can kind of disappear into the background, right? And if you wanted to, as long as you're polite and quiet, then the teacher will leave you alone, won't they? Yeah, not me. Because it's my job to make sure you learn this. Your job to learn it. So we're going to do it. All right, so let's just go through theirs. They show you that it's 20 out of 50. And that's where they stop.
We didn't simplify.
Oh boy, do we not like that. Okay? Bad education perfect. Because I would certainly count it wrong if you didn't simplify it.
Interesting. Overseas bad.
There we go. Because everybody suddenly finds interesting overseas coins in your bag, unexpectedly. Right? Okay. Okay.
And also, like, yes, the tricky if it's a fair coin.
Yes,
It might be
yes.
really unfair, and actually, like, I'm sure.
There we go. Okay, guys, come on. Focus. Let's come back. Mick finds an interesting overseas coin in his bag and conducts an experiment to see if it's a fair coin. All right. Mick was walking along and found one on the street. That would maybe make more sense. The results are shown in the table below. Can he conclude that it is a fair coin?
What do they mean by a fair coin?
Okay. What happens when you flip a coin? What do you expect to happen? You get a heads or a tails, right? Now, have you ever heard of coins that are not fair? You can order them online. You can order an American quarter or some other coins that when you flip them, they always land on heads.
Wait, why?
They weight them. So that when they're in the air flipping, when they fall, you have to flip them high enough. When they fall, they always fall on that side.
Maybe that's a trick to some
It is.
my sister.
If it's like, hey, if this light.
You can get them online. And dice the same way. They're called loaded dice. Have you ever heard that expression? So you roll the dice, and what do you always want to get if you're playing a dice game? Do you know? 7. Well, if you're rolling two die, like if you're gambling, you guys are not gamblers, right? There you go. If you're gambling and you roll, you want to roll a 7. 7 is a winner if you roll it on the first try. So they'll weight the dice so that one of them always comes up on a 1 and one of them comes up on a 6, or one of them comes up on a 2 and the other comes up on a 5, something that adds up to make 7. So not everything is always a fair thing. And if they always, because you don't think in terms of cheating. Yeah. We're all, we wouldn't cheat. So, well, think about, okay, and that's exactly where I was going. Think about, have you ever seen like Roman coins or old coins?
Yes.
They're handmade, hand-stamped, right? On one side, it may have like the face of the emperor. On the other side, some of them are just blank. If you put more metal on one side than the other, it naturally weights it, doesn't it?
Yep.
So what you can do is on one side, you can put more relief or a heavier metal inside. So it can happen.
But coins are really hard.
Well, not all coins. That's why he's finding an interesting overseas coin. Yeah. So when you think that's why they're saying he's found an interesting overseas coin, because it might not have the same properties of the coins you're used to. All right? There used to be an American coin that was one metal on one side, so it was silver on one side, and then it was gold on the other side. It was only just for the bicentennial. So things
What's Mick short for?
What now?
What's Mick short for? His name's Mick. What's it short for? Because she said Mickle and she spelled it M-I-C-K-L.
I have no idea.
Like a nickel.
Okay, so here we go. Here are the trials, and here are the results. Guys, focus. Come on back. Focus. So the first time he rolled a heads. Second time he did the tails. Third time's tails. 4, blah, blah, blah. I'm not reading that whole thing to you. Okay? So you see what he did? He just kept flipping it up. So this is an experiment, yeah?
Yes.
So he just experimented to see how many. Now, so using the results above, we can see that the probability of flipping a tail is 5 out of 8, and the probability of flipping a heads is 3 out of 8. How did he get those probabilities? Where did that 8 come from on the bottom, for example? Poppy?
He rolled it 8 times.
Yeah, he flipped it 8 times, yeah?
Oh.
Okay. And if he got a tail, and if tails is 5/8, that means that when he flipped it the 8 times, 5 of those times he got a tails. And the 3/8 means 3 of the times he got a heads. So in other words, he's just counting what happens. I got a heads. I got 1, 2, 3 out of the 8. Okay? This part just tells you how many times he did it. So don't worry about the 2 in the tails and the 3 in the tails, right? That doesn't really have anything to do with it. Here, it's the ultimate, the total count that we're worried about, and then how many times you got a heads, and then how many times you got a tails. So it's 5 out of 8 and 3 out of 8. So do you think it's a fair coin?
Yes.
Yeah, because even though they're not exactly equal, do you expect an experiment to be exactly equal? No, but they're close, right? What if he'd gotten tails 8 times? Yeah, there's no way that's a fair coin. See the difference?
We just have to test it more times.
Yeah, exactly. To be completely certain, you'd have to test more times. But I would be pretty convinced that it was not fair, even at just 8 times, because the likelihood of that happening is like me winning the lottery. Which, by the way, I don't know if I would be here tomorrow if I did, or Monday if I did. But no, I would continue to teach you, but I might do it in solid gold shoes or something. Using these results, that would be so uncomfortable. Using these results, it would appear that this is not a fair coin because one of them is more than the other. But in order to make a final conclusion, you just have to do it more and more and more and more. What happens, do you think, if it is indeed a fair coin? And you do the experiment enough times, what do you think is going to happen to the probabilities? They're going to merge together. They're going to get closer and closer and closer and closer. 20 times? Probably not. 50 times? Maybe, but probably not. 100 times? Maybe closer. But again, it may take 1,000,000 times before you get exactly the same number. Or you may never get exactly the same number, but very, very, very close, if it is indeed a fair coin.
So are you saying that theoretical probability is better than experimental because you still have to take longer to experimental than theoretical?
No, what I'm saying is that neither one of them is exact, ever. And you'll usually never be able to replicate theoretical probability exactly. So one is not really better than the other, and have you ever heard that statistics is used to prove any lie? If I want to prove something, I want to prove that 30% of you are going to make, the top grades or whatever. Then I could do an experiment where I'm only picking people who made the top grades to make those numbers higher or whatever. So theoretical probability is less manipulated, right? But if I wanted to prove something, I would use experimental probability. For example, if I want to prove that 100% of the Queen Margaret students take my class, then I would only pick you guys and only my other classes, and then use that as my experiment instead of all Queen Margaret students or something. So you see that, one is not more accurate than the other technically because if you did it enough, but theoretical probability can be manipulated less. Okay, so kind of you're on the right track there, and we'll look at some of those things as you move forward and you're doing experiments of your own and see what's happening. Okay, all right, good. So here we go. Calder is running an experiment. Yeah, toast sounds good. To see whether a piece of toast thrown in the air lands on the ground buttered side up or buttered side down. He runs the experiment 31 times and records his results in a table. Can anybody want to guess what do you think will happen? Do you think it'll land buttered? Always buttered side down, you think? You think most of the time? Why do you think? Okay, guys, come on. Why do you think that might be buttered side down most of the time?
Because it's like a heavier side, that there's more on it.
Right, you put the butter on it and butter's heavier, so you might work there. And besides that, isn't it just your luck?
Yeah.
That it's going to make the messiest thing is going to happen? Okay, so who knows? Well, okay, so let's look at his experiment and see what he said. So here is his experiment. The frequency is another word just meaning how often, right? Okay. All right. Yes.
It's the act of flipping it, because if you drop it, the way you drop it, it's going to land that way.
It says thrown in the air.
Oh, okay.
So he just threw it up in the air. Okay? All right. So look at it, guys. It was 13 times it was butter side up. 18 times it was butter side down. So how many total times did he do this experiment? How can I find that out? Yeah, you just add those two together and it'll tell you how many total times he did it, right? Okay, good job. Now, and this is one of your homework problems. So what is the experimental probability of a random piece of toast landing butter side up? 13 out of what? 31. Okay?
No, it's 31 out of 13.
I don't think so. Can you? You don't think so? Because 13 is contract.
What now?
Oh, we're just asking if we can simplify.
Oh, no, you can't simplify it, right? Because 13 and 31 don't have anything in common. 31 is prime. Is that it? Okay? All right. Yeah, 31 is 13. Yeah, they're both prime, aren't they? Okay? So, there you go. So the probability that's going to land butter side up is that. So then they're going to make you go through into this. So do you think that it's more likely to land butter side up or down? Our experiment shows down. Does it show it? Do you think it's strong enough to conclusion to always say down is going to happen more? Probably not. 13 and 18 aren't that different. But if you perform more experiments, what do you expect to happen? Yeah, one of them is going to get more. The butter side's probably going to get more. And again, for exactly the same reason you concluded, that the butter side's going to weigh more. So it's naturally going to do that, right? Okay? Now, unless you're in Wellington, in which case it'll land in the water. Because the wind will blow it off into no one knows where. Couldn't even ride my bike to school today because I was afraid to be blown into the water. All right, here we go. Next part. I'm going to pause the recording real quick.